Hello friends, welcome to part 4 of Quantum Mechanics and Application Solutions C-11 paper of 2022 Dibrugarh University. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. If you like my video, hit the thumbs up button. Okay, and before we start, please subscribe, and let me tell you one more thing. If you want to follow me on Insta, this is my Insta ID, Oza Lokhajit, OJHA, Oza Lokhajit, LAKHYAJIT. This is my Oza Lokhajit 123. Oza Lokhajit 123 is my Insta ID. This is my Insta ID. You can follow me on Insta. Okay, so now let's start. So we have already solved up to question number 4. Now we have question number 5a and b. So the LS coupling for an electron in 4p and 4d configuration and determine the spectral terms. Okay, so now let me give you the answer to this question 5a. So question number 5a, just wait, 5a answer. So spectral term for LS coupling is given by 2s plus 1 here Lj. So here 2s plus 1 is nothing but this is called multiplicity, and what does a, l and j mean? So I have mentioned here s is spin angular momentum quantum number, and L is for the orbital angular momentum quantum number, and J is the total angular momentum quantum number here. So now you see how to obtain those values for a particular configuration. So in the question that question number 5a, here you can see the given configuration is this 4pd. This is the configuration. So for this configuration, for this given configuration 4p 4d, let us assume that there is one electron, there is also one electron. So for those two we can have s1 and s2 both equal to half, right, for two electrons, spin quantum number, right? And for p the value of L is equal to 1, and 4d value of L is equal to 2, right? So value of S, this capital S, is from S1 minus S2 mod of S1 minus S2 to S1 plus S2. Okay, so now S1 S2 we have got both equal to half, so half minus half to half plus half. So half minus half is 0, and half plus half is 1. 0 to 1 means, so value of S is nothing, values of S are 0 and 1. So now value of capital L, that is given by small l1 minus l2 to capital small l1 plus l2, right? So l1 l2 we have got 1 and 2, so here mod of 1 minus 2 to 1 plus 2, so that's going to be from 1 to 3. That means 1 2 3. These are the values of L. So we have got L and S. So here you see. Now let us determine J. How to determine J? Okay. Now let me go to the new slide. Here you see we have got S is equal to 0 and 1, and L is equal to 1 2 3. First let us take 0 and 1. S is equal to 0 and L is equal to 1. So for S is equal to 0, L is equal to 1, L is equal to 1 means it is p state. So for that case J is equal to from L minus S to L plus S. So that's going to be 1 minus 0 to 1 plus 0, that is 1 to 1. That means simply J is equal to 1. So in that case the spectral term will be given by 2s plus 1 Lj. What does it mean? So s plus 1, so we are taking s is equal to 0 here, so the multiplicity 2 into 0 plus 1, that is 2s plus 1 is equal to nothing but 1. So here we have put 1 here, and for L is equal to 0, it means p state. For L is equal to 1, it means, for L is equal to 0, L is equal to 0 means S state, L is equal to 1 means p state, L is equal to 2 means D state, and so on. L is equal to 3 means F state. Okay, remember these things. Okay, so now you see here we have value of L is equal to 1, this one this is value of L is 1 here. So that means it is P state, and value of J is equal to 1. So here we have got 1. So this is the spectral term for S is equal to 0 and L is equal to 1. So now let us take 0 and 2. S is equal to 0 and L is equal to 2. Then what happens in this case? So S is equal to 0 and L is equal to 2. L is equal to 2 means D state. Okay, so here L minus S, that is 2 minus 0, to L plus 0, that is 2 plus 0. In both cases 2 to 2, that means value of J is 2, right? Value of J is 2 we have got. Then for S is equal to 0, multiplicity, that's gonna be equal to 1, right? So here we are getting 1 D. For L is equal to 2, D state, so here we have got D, right? So and value of J we have got 2, right? So hope you have understood this. Now let's go to S is equal to 0 and L is equal to 3. So S is equal to 0 and L is equal to 3. In that case J is equal to 3 minus 0 to 3 plus 0. In that case J is equal to 3, because we are getting 3 to 3. 3 to 3 means simply 3. Okay, so J is equal to 3, and here L is equal to 3 means F state. So and for S is equal to 0, as I have already told you that multiplicity is 1, so here 1 F 3. This is the spectral term we have got. So now let's take S is equal to 1 and L is equal to 1. So S is equal to 1 and L is equal to 1 means L is equal to 1 means P state. So when you have S is equal to 1, then multiplicity, that is 2S plus 1, that's going to be given by 2 into 1 plus 1, that's going to be equal to 3. Then we are getting here multiplicity 3, right? And value of J is 1 minus 1 to 1 plus 1, that is L minus S to L plus S. So here we are getting 0 and 1 plus 1 is 2, so that means 0, 1, 2. Okay, these three values are the values of J. 0, 1, 2. Okay, 0, 1, 2. So now that's why here we're gonna get 3 spectral terms. So as we have already got that multiplicity is 3 here, 2S plus 1 is 3, so here we are getting 3. And as the value of L is 1, so it is P state. So here you see, as I have written here P, right? You can see clearly, and you see we are getting 3 values of J, 0, 1 and 2. Okay, so hope you have understood this. Now let's take S is equal to 1 and L is equal to 2. Okay, let me go to the next slide. So here this is S is equal to 1 and L is equal to 2. So here for this case L minus S, that is 2 minus 1, and L plus S is 2 plus 1. So 1 to 3, that means the value of J are 1, 2, 3. These are the values, and it is D state because L is equal to 2 here, so we are writing here D. Okay, and value of S is 1, so multiplicity is simply 3. 2 into 1 plus 1, that is 2S plus 1, okay, which is equal to 3. So that's why 3D1, 3D2, 3D3, because these are the values of J, 1, 2 and 3, right? So hope you got it. So now let us take S is equal to 1 and L is equal to 3. Okay, so S is equal to 1 and L is equal to 3. L is equal to 3 means F state. If S is equal to 1, then 2S plus 1, that's going to be equal to 3. Multiplicity is 3, so we are writing here 3. So we are getting 3 values of J, 2, 3 and 4. Hope you understood how to find J. L minus 1 to L plus 1, 3 minus 1 to 3 plus 1, that is 2 to 4. 2 to 4 means 2, 3, 4, right? So here 2, 3, 4. These are the values of J, and L is equal to 3 means this is F state. F state. Okay, so these are the spectral terms. Okay, so hope you have understood this. Now let's move on to the next question. So what is the next question here? You can see 5B. Distinguish between normal and Zeeman, normal and anomalous Zeeman effect, and obtain an expression for the magnetic interaction energy for a single valence electron experiencing normal Zeeman effect. Okay, let me give you the answer here. So this is the question number 5b, and you can write the difference of normal normal Zeeman effect and you see anomalous Zeeman effect from these two paragraphs, right? And next part of the question, that is expression for the energy, magnetic interaction, expression for the magnetic interaction energy for the single valence electron experiencing normal Zeeman effect. So for that part, let me give you the answer. So you can start from here. This is the explanation of normal Zeeman effect. So here you see in terms of quantum theory, an atom possesses an orbital angular momentum, that is L vector, and orbital magnetic moment, that is mu L, with gyromagnetic ratio given by this, which is equal to 2E by M, right? This is called gyromagnetic ratio. So here E and M are the charge and mass of electron, okay, and this vector is directed opposite to the L vector. Let me show you. So here you see this is the L vector and this is the mu L. These two are opposite. So these two vectors occurs when this electron is revolving in this orbit. This is the orbit, right? Now you see when the atom is placed in an external magnetic field B. So here you see this is the direction of magnetic field B. It is along z axis, okay? So this atom in which this electron is moving in this direction in this orbit, as you can see, that is placed in a magnetic field as shown in this figure, right? The vector L presses around the field direction, okay? This vector will presses in this way, right? That means this one, this is the vector, okay? About the magnetic field it will precess, that means this is the precision, like this, okay? Hope you have understood this. Just wait, let me clean this. Now you see which quantized component given by Lj is equal to this. Let me show you in the next page. So here this is the value of Lj, ml is by 2 pi, right? So this ml is nothing but magnetic orbital quantum number. This is called magnetic orbital quantum number, and its the value of this is values of ml given by L comma L minus 1 comma dot 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 minus L, right? That means you can say that ml is given by the values from plus L to minus L, okay? And that is total of 2L plus 1 values, okay? Total number of values is given by 2L plus 1. This precision is known as Larmor precision, and it means that in a magnetic field its level, L level, is split into 2L plus 1 levels, okay? In you see it's characterized by the magnetic orbital quantum number, and Larmor's theorem, the angular velocity of precision is given by this expression, right? This is the angular velocity, okay? The interaction energy of its such precision is equal to the product of the angular velocity and the projection of L and along the field, right? So projection of L along the field, that means Lz, this z component of this L vector, okay? And the angular velocity, that is omega. So their product gives the energy, okay? So this is the required expression, and in terms of wave number we can write this way, okay? Interaction energy is given by this. So hope you have understood this, okay? So thank you for watching. See you in the next video, okay? This paper is completed.